This slidecast will cover binary search trees. Now recall the definition of a binary search tree. A tree is a binary search tree if T is empty, or if it's not empty, its root node has 0, 1, or 2 non-empty subtrees. And the left subtree is a binary tree that has all values less than the value in the root of T, and its right subtree is also a binary search tree, and it has all values greater than the value in the root of T. And we will assume that all entries saved in a binary search tree are unique, so there are no duplicates. Here's an example of a binary search tree. And notice, here's a tree. The root node has the data value lay, and the left subtree is a binary search tree. Every value here in this left subtree is less than lay. It means that so if we place these in dictionary order, all these terms would come before lay, and all the terms here in the right subtree would come after lay. And if you examine this tree, you'll see that every subtree is itself a binary search tree. Now, a recursive algorithm to search a binary search tree is the following. If the root is null, then the item is not in the tree, so we return null. You compare the value of target with root arrow data, and if they're equal, we've found the target, and you return the data at the root. If the target is less than the root data, then you return the result of searching the left subtree, else return the result of searching the right subtree. So these are our recursive definitions here. So suppose we're looking for Jill in this binary search tree. We begin by looking at the root, and since Jill is less than lay, J comes before L, then we'll do a binary search on the left subtree. Jill is greater than house, so then we'll search the right subtree. Since Jill is greater than Jack, we'll search the right subtree again. Now finally, Jill is less than killed, so we'll search the left subtree here. And in the case of kept, Jill comes before kept, so we'll search the left subtree again, and this left subtree is null, and so we'll get a result of not found. So searching a tree is generally an order log n operation, and if a tree is not very full, performance will be worse. And if we have a search tree, kind of a worst case scenario where a tree only consists of right subtrees, then it'll approach order n. But if the tree is close to being full, is a full tree or very close to it, then we'll approach our order log n performance. So the binary search tree class, here are some functions. We'll have an insert and an erase function to add and remove items from the tree, and then we'll have a find function where we'll look for a target, and it will return, a pointer to that item if it's found, null otherwise. Here's some UML diagrams showing the binary tree class with the following public methods to get the left and right subtrees, get the data, and do a toString. And here's a binary search tree which inherits from a binary tree. So remember, a binary search tree is a specialized kind of binary tree that has things ordered. And then a binary tree has nodes. And so here's this has a relationship, and our BT node has data and then left and right field values that are pointers to nodes. Here's our binary tree.h file that the author provides. It's a template class. Here has some of the constructors and these operations we just described. You can take time and look over this code on your own. It's contained in your book, and you should become familiar with it. Be sure you understand every line of code in the book. If not, bring your questions to class. So here's a find function, which is a pointer to a node and then a target value to search for. And here's a replace parent function. Now here's a recursive algorithm for inserting a new item into a binary search tree. If the root is null, then we replace the empty tree with a new tree with the item at the root and return true. If the item is equal to the root, then the item's already in the tree and will return false. Remember earlier, we won't consider trees with duplicate entries. Now if the item is less than the root, then we recursively insert the item in the left subtree. Otherwise, we recursively insert the item in the right subtree. So here we're going to insert Jill into this tree. And remember, this follows the same search path we saw earlier when we had the example of searching for Jill. Only now when we get to kept, Jill is less than kept. So we'll recursively insert into the left subtree. And since the left subtree is null, we've reached a leaf node. And so we'll now insert a new node at this location with the value Jill. Here's an implementation of the insert function. And this insert method is a wrapper method, where we call it with a single parameter, the item to be inserted. And this turns around and calls insert again. This is the two parameter variation, where we pass the root of the tree as a parameter along with the item. And then this is the method that we will call recursively. If the local root is null, then we're at a leaf and we'll insert a new node at that location. Otherwise, we'll either insert into the left or right subtree depending on how the data item compares to the current item in the root. Now if the item is to be removed is a leaf node, then its parent reference is set to null. But if an item to be removed has only one child, then the grandparent references the remaining child instead of the child's parent, because the parent is the node we want to remove. So here's an example of removing from a binary tree, and we're going to remove the value is. And to begin with, is the parent of the node in. Once we find it, since there's only one child, we'll remove is, and in will take its place. Now if the item to be removed has two children, then we'll replace it with the largest item in its left subtree, which is its in-order predecessor. So if we're removing house, which is this sort of internal node, then in its left subtree we find the largest item, which is its in-order predecessor, and we'll move horn from this leaf position up to where house was located. Here's an example of removing rat. So rat starts out occurring in this position. We have to find its largest in-order predecessor, and in this case that's going to be priest. Priest has one left child, so priest is going to be to replace rat, and then mourn will go and take its parent's location. Here's a recursive algorithm for removing from a binary search tree. If the tree is null, then the item was not in the tree, so we return null. We can compare the item to the data at the local root, and if the item is less than the data, then we return the result of deleting from the left subtree, and if it's greater, then we return the result of deleting from the right subtree. Otherwise, we've located the item, and if the local root has no children, then we set the parent of the local root to reference null. Okay, so we removed a leaf node. And if the local root has one child, then we set the parent of the local root to reference that child. Otherwise, here's the case with two children, and we need to find the largest in-order predecessor. So if the left child has no right child, then it is the in-order predecessor. So we set the parent of the local root to reference that left child. Otherwise, we find the rightmost node in the right subtree of the left child, and we copy its data into the local root's data and remove it by setting its parent to reference its left child. Here's an erase function, and here's the case where the item, if it's less than the data at the local root, here's where we're making a recursive call to remove it from the left subchild, and here we make the recursive call to remove from the right subchild. And if we found the item, here's the logic that does the operations just described. You should stop the slidecast and study this code. Now the replace parent function, remember this was the case where we take mourn and replace priest, which had been copied to where rat occurred before. Now here's the replace parent operation. If the local root arrow right is not null, then we call replace parent, passing a parameter of the old root and the local root arrow right. Otherwise, the old root data, we get replaced with the local root data. The old root is set equal to the local root, and local root is set equal to local root arrow left. Now in the preceding figure, the recursion stops with old root pointing to the node with the value to be removed, which is rat, and the left child of the node to be deleted has a right child, priest, which is its largest child. The local root references the node priest. Old node arrow data will contain priest, replacing rat, and old root is changed to point to priest. The node mourn, the left child of priest, becomes the new right child of milked. So to test a binary search tree, verify that an in-order traversal displays the tree contents in ascending order after a series of inserts and deletes are performed. Now, a problem to solve is to write an index for a term paper, and the index should show each word in the paper followed by the line number on which it occurred, and the words should be displayed in alphabetical order. If a word occurs on multiple lines, then the line numbers should be listed in ascending order. Now, to solve this problem, we could store each word and its line number as a string in a tree node, and two occurrences of C++ on lines 5 and 10 would be stored as the following strings. And each word will be stored in lowercase to ensure that it appears in its proper position in the index. And the line number is right justified so that the string C++5 is less than the string C++10. Now, if the leading spaces were removed, this would not be the case. C++5 is greater than C++10. Now, after all the strings are stored in the search tree, we can display them in ascending order by performing an in-order traversal. And storing each word in a search tree is a log-n operation, where n is the number of words currently in the tree. And storing each word in an order list is an order n operation. There's some code in your book that gives a program for writing an index for a term paper. You should go study this on your own and see that you understand this code. I'm not going to walk through it for you here in the Slidecast. But here's a program to generate a simple index, and it tokenizes all the words and moves them to lowercase. Here's the string tokenizer class. So go into your book, or you can pause the Slidecast and study this code, and bring your questions to class about how it works. Now, to test this, we could write a main function that declares a new input stream and binary tree string objects, and the input stream can reference any text file stored on our hard drive. And you can make sure that duplicate words are handled properly, that words at the end of each line are stored in the index, empty lines are processed correctly, and the last line of the document is also part of the index. And that brings us to the end of this Slidecast.